Hey everybody, it's Mr. Dean here. I need your help. We need to guess the mystery number. There's a missing number. I want you to find it. Ready? Go. 16 times something is 48. All right, that was pretty easy actually. Maybe you already got it. 3. All right, well, I got a harder one. Here it comes. 112 times 851 times something is 70,816,816. What do you think? Get your calculator, I'll give you a few seconds here. Pause the video. I'm going to give you the answer really quick. Are you ready? 112 times 851 times 743. That's right. So how might you do that? That was a little harder. How might you do that? I'd probably take this giant number, put it in my calculator, divide by that, and then divide by that. And that's probably how you got this first one. You probably did it mentally, 48 divided by 16, or maybe you kind of thought forward, 16 times something, but in the back of your head, you were really doing division. All right, I got a tougher one now. There is two integers that multiply to 28,233,463. Now, by non-trivial, I mean just not including 1 times 28,233,463. All right, two integers that multiply to that number. This is the key to the internet, believe it or not. I'll give you a few seconds. You can pause the video if you need more time. That's sort of what it looks like, all right? Come up with two different, maybe they're the same integer, but two different integers in this case. All right, any takers? Let's see what you got. Did you get 4,231 and 7,673? Probably not. And that is one of the keys to how the internet is encrypted. Public key encryption is born of mathematical observation. It's easy to multiply two prime numbers together. These are prime numbers, by the way. And it's easy to multiply those together to get a third number that is almost prime. And it's much, much harder to work backwards and figure out what these two original prime numbers were by looking only at this third number. All right? And this ensures that encrypting data, which relies on multiplying primes, is easy. So we're ready for the real zeros of polynomials. Decrypting these primes requires these prime factors, and it's so difficult that it's impractical even with the speediest supercomputers. And where these prime numbers come from and how do computers avoid patterns so other computers can figure it out, all has to do with this idea of RNG, random number generators. And there's so much math behind it. It's a pretty cool area and branch of mathematics. But let's get to the basics of what we're doing. Real zeros of polynomial functions. We're trying to find zeros of polynomial functions. And what we're going to do here is we're going to take this polynomial and we're going to try to see if x minus 3 divides into it. In other words, we're trying to see if 3 goes into this and makes it a 0, if 3 is a 0. And we got two ways of doing this. One is long division, and one is synthetic division. I don't know how much you've been exposed to synthetic division. Even long division gets a little hairy. We haven't taught it too much in Algebra 2, so let's take a look at this now. So long division, you take your x minus 3 and you divide it into this, and you want to notice, very important, that you have a placeholder for x squared. Because looking back at your function, there are no x squareds. So in terms of going down the exponent trail from x to the third, x squared is really x to the first. Of course, this one, in a sense, is x to the 0. You want to have a placeholder. You want to have a coefficient for each of the variables. So we got to have a 0 there. That's important. Next thing is we think, all right, just like long division for regular numbers, how many times does x fit into 3x cubed? All right, we put that answer up top. Turns out if I take out the x, I got 3x squared. Put that on top. All right? And then, if you remember how long division works for regular numbers again, we take that 3x squared and we multiply it by each of these things here. So we got 3x squared times x gets 3x cubed. 3x squared times negative 3 gets negative 9x squared. All right. Now remember, again, just like regular old long division, we actually subtract that away from our answer up above in black, and we subtract away, so these cancel out, and we're left with actually a positive 9x squared, right? Because a negative minus, those turn out to be positive 9x squared. And then we do it again. We think, right, how many times does x fit into 9x squared? And you remember the idea, we bring down this minus 7x. So how many times does x fit into 9x squared? It's positive 9x. And then we multiply that times everybody over here, these two things, distributed in a sense. And I take it away and subtract it. And we get negative 9x squared minus negative 27x. And we're just very careful with the minusing and the addition and so forth. And we bring down the 5. And we do it one more time. How many times does x go into 20x? Well, that's 20 times. And we multiply that all the way through times the x minus 3. And I get negative 20x minus 60. And when I finally realize that those cancel, I get a 65 down the end here. Now that's the remainder. If you remember way back when, put a big R, remainder. The way that looks is, if I can get this in here, well, okay, not working. We write 65 over our factor of x minus 3. All right? So our answer to this problem, that's why they call it long division. It took a while. And we finally get an answer. So it did not go in perfectly. We had a remainder. All right? We had 3x squared plus 9x plus 20 plus 65 over x minus 3. That's the entire answer to the long division. Now let me show you synthetic division and why it'll be clear why we like synthetic division so much. Synthetic division doesn't take up as much room. It's a neat little kind of artificial way of doing it. What we're going to do to start with, as you can see, we write the zero of that factor out there. So it's x minus 3, but I put a positive 3 on the outside because that is the zero of that factor. And then I only take the coefficients of what I'm dividing, and I remember that I need to have, very important, this is the one thing that's forgotten sometimes, I need to have that placeholder for, in this case, I'm missing an x squared, so I need a 0 there. All right, and then I kind of do this kind of upside down division symbol in a sense, and I leave some space. I'm going to put some numbers under these numbers here. All right, now here's how it starts. You bring down the 3. You bring down whatever that first number is, whatever it is, you just bring it down. And now we do 3 times this 3 times this 3. All right, multiply that. And I put that answer here, and I add down. I get 9. And then I'll keep on going with that. I'll take this 9, and I'll multiply it by this 3, and I'll get 27. Add down, and I get 20. You might recognize these coefficients from the previous problem. And then I'm going to take that 20, follow the pattern, and I'm going to multiply it by 3. And I get 60, and I add down, and I get 65. 3, 9, 20, and 65. Do you recognize those? Those come from the coefficients of our answer. So all we need to do in synthetic division, if we're going to use synthetic division instead of long division, is I need to remember that my last number is the remainder, and every coefficient up from there kind of adds another exponent to x. So in other words, this is my remainder. I would write it as 65 over x minus 3. And then the 20 is the constant. 9 represents the number of x's to the first power. The 3's represent the number of x's squared. If I had more numbers in front of the 3 for some other problem, I would just keep on going to be like 4x cubed or whatever it might be. All right, whoops, but we don't have that to worry about. All right, so our answer is the same whether I use this fancy synthetic division or I use the long division. All right, your choice. But synthetic division really, as you can see, obviously quicker, and there's less multiplying to worry about. And the only thing we need to remember in synthetic division is that placeholder. That seems to be the one problem that kids come about. And also students have a little bit of a problem figuring out what the exponent is for each of the coefficients, all right? Another way to kind of remember it is if you're dividing from the very beginning back here, if you're dividing 3x cubed by an x, then your leading term is going to have x squared because you're taking an x out of that 3. So your leading term is going to be x squared. That's another way to kind of remember how the exponents work. All right, so there's synthetic division and long division. A couple of new facts over here is that factor theorem. We just found out that x minus 3 is not a factor since there is a remainder, and the remainder was 65. If the remainder was 0, then x minus 3 would be a factor, and also the number 3 would be a 0 of the equation. So we would even know that the graph would go through 3 somehow. All right. That's related to the remainder theorem. Both of these go hand in hand. If the function is divided by some kind of factor, in this case it was x minus 3, that the remainder is what you found when you put that number in. In other words, I found the remainder is 65. Turns out that if I plugged 3 into that giant equation I had earlier, into that function, if I plugged in 3 and I cubed it and did all that other work, I'd end up with 65. So the remainder and the value at that spot, at that 0, are actually equivalent. All right? And we can use both of these theorems in our work. So let's get right to another example here, give you some practice. So here's a different function. I'm going to just see if x minus 5 is a factor of it, and we're going to divide it out. So I'll use synthetic division. So I'll bring the 5 out in front. That comes from there. And each of these coefficients, it looks like I do not need a placeholder. So I'm just going to use those numbers, kind of extend that, and here goes. Sometimes people have a hard time starting it. It's pretty easy, though. Just remember that you bring down that first number, and that's kind of seeds the whole problem. I'm adding down. Remember, in long division, you're subtracting as you go down, so don't be confused there. I'm adding down. Oh, look at this. I have a 0 remainder. All right? That means a couple of things. First of all, this divides in evenly, and it means that 5 is a 0 of this function. It means if I plugged in 5 for x, I would get out 0. It also means that after I take out that one factor, I know other factors. I put back all my numbers here. I know that this goes into my original green function. All right? And then I could attempt to continue to factor this to see if I can get all the factors. All right, I'll do this. Let's see. 3x squared might be 3x and x, right? And I need to find, it's either a combination of 1 and 5 or 5 and 1. So I'll try 5, and I'll try 1, and I think it works out. So 3x squared, in between term will be negative 2x, and final term, final term will be not plus 5. All right, so it does not factor to be that. In fact, I think it is unfactorable is my guess right there. So either way, we found out that 5 is a 0, and we might have found out that there are no other zeros for it. Here's another example, and this is already all worked out. Save you some time here. You can just take a look at it, pause the video if you need to. But in green, I have 5x cubed plus 18x squared plus 7x minus 6, and we're dividing it by x plus 3. So just to show you here, I'm dividing by x plus 3. So that's why I have a minus 3 on the outside of my synthetic division. I have all the coefficients here ready to go. There is no placeholder again for this particular example. And I multiplied it all out. In this case, I did again, got a remainder of 0. And what that means is if I plugged in negative 3 into my function, I would get out 0. And in this case, it was factorable. I got 5x squared plus 3x minus 2. And then that factors out to be 5x minus 2 and x plus 1. All right? So all my zeros all together there were as many as 3 zeros. It's going to be 3 real zeros here. And the zeros are, let's see, zeros are 0, nope, sorry, -3. Let's see, I got a 0 here at -1. And the 0 of this factor, remember, you have to set that equal to 0 and solve it. It'll be positive 2/5. So those are the 3 zeros for this function. We've completely factored it. All right. Remember in the beginning we were trying to figure out like the factors of this giant number. Well, in this case we did it pretty well for a cubic function, and we split it into all 3 factors. All right. Those all 3 factors would be these 3 factors generating these 3 zeros. All right. Hey, guess what? That's the end of part 1. Part 2, I'm sure you're very excited about, coming up next. Take care. We'll see you.